Welcome to DAR Tutors. We provide expert tuition for students taking IB, A-Level, and IGCSE curricula. Today, we're focusing on a core principle in IB Chemistry Higher Level, Hess's Law. By the end of this session, you will be able to state and apply Hess's Law to calculate enthalpy changes for reactions that cannot be easily measured directly. You'll be able to work through problems using both energy cycle diagrams and the algebraic method. These are critical skills for the HL exam. Before we dive into Hess's law, let's establish why we need it. Imagine you want to know the enthalpy change of a reaction, but you can't measure it directly. A classic example is the decomposition of calcium carbonate into calcium oxide and carbon dioxide. This reaction is slow and requires a high temperature to go to completion. A direct experiment would be impractical or give unreliable results. Similarly, if we consider the incomplete combustion of graphite, the reaction can produce both carbon monoxide and carbon dioxide. This makes it impossible to isolate the enthalpy change for the formation of only carbon monoxide. So how can we determine the enthalpy change for these kinds of reactions? This is precisely where Hess's law becomes an indispensable tool. It provides a way to calculate unknown enthalpy changes using known measurable ones. Now, let's formally define Hess's law. It is a statement of the first law of thermodynamics, which is the principle of conservation of energy. Hess's law states that if a reaction is carried out in a series of steps, the enthalpy change for the overall reaction will be the sum of the enthalpy changes for each individual step. The key idea here is path independence. The overall enthalpy change depends only on the starting materials and the final products, not on the specific sequence of steps that gets you from one to the other. We can visualize this with a simple cycle. Imagine converting state A to state D. You can do this directly, via route 1, with an enthalpy change of delta H1. Or you can take a detour through states B and C via route 2, with a total enthalpy change of delta H2 plus delta H3 plus delta H4. According to Hess's law, the total energy change must be the same, so the sum of the changes in route 2 is equal to the change in route 1. This fundamental principle allows us to connect different reactions and solve for unknown enthalpy values. To successfully use Hess's law, you need to master two algebraic manipulations of chemical equations. First, if you reverse a reaction, you must reverse the sign of its enthalpy change. For example, if the formation of water is exothermic, the decomposition of water must be endothermic. Second, if you multiply a reaction by a coefficient, you must multiply the enthalpy change by the same coefficient. Doubling the amount of reactants and products doubles the energy change. It's important to note the standard conditions, indicated by the Plimsoll symbol. These are a pressure of 100 kilopascals, a 1.0 molar concentration for solutions, and a specific temperature, usually 298.5 Kelvin or 25 degrees Celsius, which must be stated. Let's apply these rules to our first example, the combustion of diamond. Our target equation, which we want to find the enthalpy change for, is the combustion of solid diamond to form carbon dioxide gas. We can't measure this directly, but we are given two reactions that can help us. The first is the conversion of solid diamond to solid graphite, with an enthalpy change of -2 kilojoules per mole. The second is the combustion of solid graphite to carbon dioxide gas, with an enthalpy change of -393 kilojoules per mole. We can solve this algebraically. Our goal is to manipulate the given reactions to add up to our target reaction. Notice that diamond is on the reactant side in our target reaction, and it's on the reactant side in our first given reaction. So we'll use reaction 1 as is. It also contains graphite on the product side. Next, reaction 2 contains graphite on the reactant side and carbon dioxide on the product side, just like in our target. So we'll use reaction 2 as is. Now let's add these two reactions together. We can see that solid graphite appears on both the reactant and product side. We can cancel it out, just like in algebra. The resulting equation is our target equation. This means we can find its enthalpy change by simply adding the enthalpy changes of our two manipulated reactions. So, the enthalpy of combustion for diamond is -395 kilojoules per mole. We have successfully calculated an enthalpy change that is difficult to measure experimentally. Let's try another example. This time, we'll calculate the enthalpy change for the oxidation of hydroquinone to quinone. Our target reaction is hydroquinone reacting with hydrogen peroxide to form quinone and water. We are provided with three other enthalpy changes. First, hydroquinone converting to quinone and hydrogen gas. Second, the formation of aqueous hydrogen peroxide from its elements. Third, the formation of liquid water from its elements. We'll again use the algebraic approach. Let's find each component of our target equation in the given reactions. Hydroquinone, C6H4OH2, is on the reactant side of our target and also in reaction 1. Quinone, C6H4O2, is on the product side of our target and also in reaction 1. So, we will use reaction 1 as is. Reaction 1 is used without any changes. Next, we need hydrogen peroxide, H2O2, on the reactant side. Reaction 2 has H2O2 as a product. To get it on the reactant side, we must reverse the reaction. When we reverse reaction 2, its enthalpy change becomes positive 191 kilojoules per mole. Finally, we need 2 moles of liquid water, 2H2O, on the product side. Reaction 3 gives us 1 mole of water. To get 2 moles, we need to multiply the entire reaction by 2. Multiplying reaction 3 by 2 also doubles its enthalpy change to negative 572 kilojoules per mole. We have now found a path. Let's add the manipulated equations together. Adding our 3 new equations gives us this combination. We can see that 2 moles of hydrogen gas on the product side of reaction 1 and reaction 2 cancel with 2 moles of hydrogen gas on the reactant side of reaction 3. Also, 1 mole of oxygen gas on the product side of reaction 2 cancels with 1 mole of oxygen gas on the reactant side of reaction 3. What we're left with is our exact target equation. Now we just need to add the corresponding enthalpy changes. The final answer is negative 204 kilojoules per mole. You can see how this algebraic method is systematic and powerful. Now, let's look at another method for solving these problems, which is often more intuitive for some students. The energy cycle diagram. Consider the decomposition of calcium carbonate, our initial problem. The problem provides us with reactions of both calcium carbonate and calcium oxide with hydrochloric acid. Reaction 1 is calcium carbonate plus hydrochloric acid gives calcium chloride, water, and carbon dioxide with an enthalpy change of negative 17 kilojoules per mole. Reaction 2 is calcium oxide plus hydrochloric acid gives calcium chloride and water with an enthalpy change of negative 195 kilojoules per mole. To construct the cycle, we place the components of our target reaction at 2 points on the diagram. We can put the reactants, calcium carbonate, and the products, calcium oxide plus carbon dioxide, at the top corners of a triangle. The arrow pointing from reactants to products represents our target enthalpy change, delta H. The common pathway, the products of the given reactions, forms the third point of the triangle. In this case, it's the aqueous calcium chloride in liquid water. Now we draw the arrows for the known reactions on the cycle. Reaction 1 goes from calcium carbonate to the common products. Reaction 2 goes from calcium oxide to the common products. Note that for reaction 2, we need to also include the hydrochloric acid and carbon dioxide from the other side of the triangle to balance it. But the enthalpy change is just for the reaction itself. Hess's law tells us that following the path around the triangle in one direction must give the same enthalpy change as following it in the other direction. Let's trace our path. Our target path, which we'll call Route A, is from reactants to products. The known path, Route B, goes down the left side, across the bottom, and up the right side. The total enthalpy change for Route A must equal the total enthalpy change for Route B. When traversing the known arrows, we must follow their direction. If we go against an arrow's direction, we must reverse the sign of its enthalpy change. Following our path, we use reaction 1 as is, so its enthalpy change is 17. But we must go up the right arrow, which is against the direction of reaction 2. Therefore, we use negative of delta H2, which is positive 195. Summing these gives us a final answer of plus 178 kilojoules per mole. So far, we've focused on using other reactions to find an unknown enthalpy change. Now, let's introduce 2 important types of standard enthalpy changes: combustion and formation. Standard enthalpy of combustion, or delta Hc, is the enthalpy change for the complete combustion of 1 mole of a substance in excess oxygen. All reactants and products must be in their standard states. For example, the complete combustion of 1 mole of methane gas. Standard enthalpy of formation, or delta HF, is the enthalpy change when 1 mole of a compound is formed from its constituent elements. Again, all substances must be in their standard states. There are two crucial points about delta HF. First, the standard enthalpy of formation of an element in its standard state is, by definition, 0. There is no enthalpy change in forming an element from itself. Second, for allotropes like oxygen gas and ozone, only the most stable form, O2, has a delta HF of 0. Ozone, O3, is less stable, so it has a non-zero delta HF. We can calculate the enthalpy change of any reaction using the standard enthalpies of formation of its reactants and products. The formula is delta H of reaction equals the sum of the standard enthalpies of formation of the products minus the sum of the standard enthalpies of formation of the reactants. Remember, for each substance, you multiply its delta HF by its stoichiometric coefficient from the balanced equation. Let's apply this to find the enthalpy of combustion for propane, C3H8. First, we write the balanced equation for the combustion of propane. 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of liquid water. Now we need the standard enthalpies of formation for each substance involved. These values can be found in your IB chemistry data booklet. From the data booklet, the delta HF of propane is -104, carbon dioxide is -394, and water is -286 kilojoules per mole. Remember, the delta HF of oxygen is 0. Now we substitute these values into our formula. The products are 3 moles of carbon dioxide and 4 moles of water. The reactants are 1 mole of propane and 5 moles of oxygen. Plugging in the numbers, we get the sum of products minus the sum of reactants. This simplifies to -1182 minus 1144, all minus -104. So the standard enthalpy of combustion for propane is -2022 kilojoules per mole. This method is incredibly powerful for finding enthalpy changes of a vast number of reactions. Before we move to practice questions, let's take a brief moment. If you're finding this content helpful and are looking for expert one-on-one support in your IB, A-level, or IGCSE chemistry studies, we invite you to contact DAR Tutors. Our experienced tutors can provide personalized guidance to help you master challenging concepts, improve your grades, and achieve your academic goals. Let's put what we've learned into practice with some IB-style questions. First question. Calculate the standard enthalpy of hydration of anhydrous copper 2 sulfate using the following data. Notice this question provides a Hess's law cycle. The cycle shows the dissolution of both the anhydrous and pentahydrate forms of copper sulfate. We need to find the enthalpy change for the hydration reaction, which is from the anhydrous solid and 5 liquid waters to the pentahydrate solid. Solution. Let the enthalpy of hydration be delta H. The cycle shows that the path through the bottom, delta H1, must be equal to our target path, delta H, plus the path up from the bottom on the right, which is the reverse of dissolution, or positive 66.5. Rearranging this gives delta H equals 11.7 minus 66.5, which equals -54.8 kilojoules per mole. This is an exothermic process. Question 2. Given the following enthalpy changes for sulfur, sulfur dioxide, and sulfur trioxide, find the standard enthalpy change for the reaction of sulfur with 1.5 moles of oxygen to form sulfur trioxide. Here we'll use the algebraic approach. Our goal is to add up the two given equations to get our target equation. Let's add the two equations together. The reactant side becomes sulfur solid, oxygen gas, sulfur dioxide gas, and half an oxygen gas. The product side becomes sulfur dioxide gas and sulfur trioxide gas. We can cancel sulfur dioxide from both sides. We also combine the oxygen terms. O2 plus 1 O2 gives 32O2. This matches our target equation perfectly. So, we just add the enthalpy changes together. Question 3 involves the reduction of iron ore. Calculate the standard enthalpy change for the reduction of iron 3 oxide to iron using carbon monoxide. Again, our strategy is to manipulate the given reactions to match the target. We'll find a home for each reactant and product. Let's start with iron 3 oxide. It's on the reactant side in both our target and reaction 1, so we'll keep reaction 1 as is. Now let's look at solid iron. It's on the product side of our target and the reactant side of reaction 2. So we must reverse reaction 2. Reversing reaction 2 gives us iron 2 oxide plus carbon monoxide forming iron and carbon dioxide, and its enthalpy change becomes negative 11. Notice I also multiplied reaction 2 by 2. Why? Because our target reaction produces 2 moles of iron. Now let's add our modified reactions. The reactants are iron 3 oxide, 1 CO, 2 FeO, and 2 more CO. The products are 2 FeO, 1 CO2, 2 Fe, and 2 more CO2. Iron 2 oxide cancels from both sides, and we combine the carbon monoxide and carbon dioxide terms. We have our target equation. So we add the enthalpy changes. 3 plus 22, which gives a total enthalpy change of negative 25 kilojoules per mole. Question 4 asks for the thermochemical equation for the standard enthalpy of formation of solid sodium oxide. The definition of standard enthalpy of formation is key here. It's about forming 1 mole of a compound from its elements in their standard states. So we start with 1 mole of sodium oxide as the product. Next, we write the constituent elements as reactants in their standard states. For sodium, the standard state is solid sodium. For oxygen, it's diatomic oxygen gas, O2. Finally, we must balance the equation to form only 1 mole of the product. This means we'll likely need to use fractional coefficients. To get 2 sodium atoms, we need 2 moles of sodium. To get 1 oxygen atom, we need 1/2 mole of diatomic oxygen. The final balanced equation is 2 Na solid plus 1/2 O2 gas forms 1 Na2O solid. Our final question for today. The standard enthalpy of formation for ammonia gas is negative 46.1 kilojoules per mole. Is ammonia stable relative to decomposition into its elements at 298 Kelvin? Explain your reasoning. This question tests your conceptual understanding of enthalpy of formation. The fact that the standard enthalpy of formation is negative tells us that the formation of ammonia from its elements, nitrogen and hydrogen, is an exothermic reaction. This means the products, ammonia molecules, have a lower total enthalpy than the reactants, the separate nitrogen and hydrogen atoms. A substance with a negative enthalpy of formation is considered thermodynamically stable. The negative value of delta HF indicates that ammonia is energetically more stable than its constituent elements in their standard states. This makes it unfavorable for ammonia to decompose back into nitrogen and hydrogen. An important distinction to make here is between thermodynamic stability and kinetic stability. While ammonia is thermodynamically stable because of its favorable enthalpy of formation, it is kinetically stable at room temperature. This is due to a high activation energy barrier that prevents the rapid decomposition into its elements. Let's quickly recap what we've covered today. We started by understanding why Hess's law is necessary, to find enthalpy changes for reactions that cannot be measured directly. We learned that Hess's law states the enthalpy change of a reaction is independent of the path taken. This allowed us to construct energy cycle diagrams and use an algebraic approach to solve problems. We also defined 2 crucial types of standard enthalpy changes: the enthalpy of combustion and the enthalpy of formation. Understanding these allows us to use the sum of products minus sum of reactants formula, which is a powerful tool for calculating many reaction enthalpies. The ability to apply Hess's law using both methods is a critical skill for the IB Higher Level Chemistry exam. Keep practicing these types of problems to build your confidence and mastery. Thank you for watching. We hope this session on Hess's law has been clear and informative. Remember, for comprehensive support in IB, A-Level, and IGCSE chemistry, including one-on-one tuition tailored to your learning style, contact DAR Tutors. Visit our website at www.dartutors.com to learn more about how we can help you succeed. We look forward to supporting your chemistry journey.